Welcome back, everybody. We're talking about infinite series right now, and we left something at the end last time. It's called the comparison test. We used it to show the divergence of the harmonics series, and we never mentioned what it was. But so suppose you have 0 less than a sub k less than b sub k for every k past a certain point anyway. Then if the bigger sequence series converges, so does the little one. If the bigger one converges, so does the little one. We used it the other way around. We showed that the little one diverged, and then so therefore the harmonic sequence had to diverge as well. So what we're doing right now is we're asking two questions. One, about series. Does the series converge? And two, if so, what's the sum? And so those are the two questions we're going to be asking for the next at least 3 or 4 sections for a while. We're going to be asking those questions for a while to come. And this leads to amazing results. And in order to do that, we're going to do something called an integral test. But first, well, let's just make some assumptions. Here's a theorem. A series of non-negative terms converges if the partial sums are bounded. A series of non-negative terms, that series converges if these partial sums have an upper bound. And the partial sums, if you recall, is a sequence. This is a sequence. The sequence has an upward bound. If that has an upward bound, that thing's going to converge. And so here's an example. We're going to use this as well as the comparison test for this example. And there's a caveat here. I want to show the series 1 over n factorial converges. And I just want to point out something, deficiency, I suppose, of the class so far. I was pointing out to me that I gave you a homework problem with a factorial, and it's nowhere to be found in this book. I looked at it in the index. It's not even in the index. So therefore, factorial is not even. Although they assume you know this, because this is an important series right now, as you will come to know. So we want to show a convergence, but first, note factorial. N factorial is, we'll go up, 1 times 2 times 3 times 4 times n minus 1 times n. That's what that's what n factorial is. And I'm going to use, I'm going to create another series which is strictly greater than this one, and it's going to converge. And so that's what's going to happen, and I guess I'll rewrite. Let's start over here. N factorial is 1 times 2, let's go 5 of them. And now this is what I'm going to create. I'm going to create one which is absolutely less than n factorial. This is less than 1 times 2 times 2. times another 2 times another 2. So the factorial is way bigger because we're multiplying by 3, by 4, by 5 instead of 2's. And this, if I keep multiplying, this is of course 2 to the n minus 1 times 2 to the n minus 1. And so therefore, if I flip them, so 1 over n factorial is actually strictly greater than. Right, 1 over 2 to the n minus 1. That's what's going on. Right. And this I'm going to show converged. So now it's a matter of stop. It's a matter of showing 1 over 2 to the n minus 1 converges. And this is a geometric series. So the sum is a over n, 1 minus r. And so what's a? Well, a is the first term. A is, let's see if I put a 1, and r is a half. So the sum is 1 over 1 minus a half, or 2. The sum of this this sequence has a partial sum of 2, so this is going to converge. Therefore, the lesser one will converge by the comparison test. And further, it's upper bounded by 2. This will never ever, the series will never be greater than 2. This will always be less than 2, not even equal to, actually. And further, just for future, again, it's upper bounded by 2, so therefore it converges by the theorem we just had. It converges, and we're going to show that the partial sum is actually e minus 1, which is 2.718 minus 1, which is 1.718. And so that's the stuff that's going to happen as we continue to our study of infinite series. Let's stop there. Stop. Boom.